My name is Ben Eggleton and I'm a Professor of Physics at the University of Sydney, and I'm also the Director of KUDOS, which is a centre of excellence that deals with optics and photonics. And we all know that mobile phones, the internet, all of these communications technologies that we deal with every day, it's all held together by a very sophisticated fibre optic network. And at the heart of that network are strands of silica glass fibre optic cables that are really the wires for the bandwidth in these communication systems. If you've never seen an optical fibre, you'd be surprised because it looks very much like fishing wire. It roughly is 100 microns in diameter. That's equivalent to the diameter of a human hair. And it has around it a polymer jacket that gives it some robustness and makes it more versatile in its operating environment. It's quite flexible. You could wrap the fibre around your finger. It's actually pretty strong and robust against mechanical perturbations. So fibre optics are made out of silica, and silica is glass. Glass has been around for thousands of years. It's the same material that the windows of our bedrooms are made of. Sand, essentially. It's buckets of sand that we melt to create high quality pure silica. The reason we use silica is that it can be very transparent. The loss of high quality glass can be very low. And to give you a concrete example, the state of the art for the loss of glass that we make our fibres out of. If you were to build a glass window 100 kilometres thick and look through that glass window, you could still see someone at the other end. The glass can be made very pure, the loss can be very low. Because it's glass, it's very viscous, it's like honey. When you melt it, it will draw like honey, and that's the whole basis for the fabrication of optical fibres. We can scale down so-called preforms that are macroscopic structures by heating them to the melting temperature. These can be drawn down, it's like honey melting into these beautiful uniform fibres. One of the topics that I'm most fascinated about in optics, and in particular in communication systems, are optical non-linearities, the research field of nonlinear optics. And let me explain what's going on there. If you have a light beam, a laser beam, that you send through a piece of glass, we know that the light will refract, and it may reflect and it might diffract, and we're familiar with the physics of those processes. But if the laser beam is very intense, if the field intensity is very high, then what will happen is the electromagnetic field associated with that light beam will actually distort the underlying atoms and molecular structure of the glass. It will change the properties, and that's referred to as an optical nonlinearity. Maybe a concrete example of an example of an optical nonlinearity are, and you might remember the sunglasses that were invented a few decades ago, that when you walked outside, they would darken, and so they would darken so that the sunlight would be attenuated. But if you went in a room, they would become more transparent. So it's a material that's changing its properties depending on the intensity of the light. Optical nonlinearities can be both very important and useful. For example, in the context of the sunglasses that I just described, we can also use these nonlinearities to do a range of interesting signal processing applications that I won't talk about because they're very sophisticated. But more often than not, these nonlinearities are a real nuisance, because when we send pulses of laser light through hundreds of kilometres of fibre, these tiny optical nonlinearities become very, very significant because they build up and they tend to destroy the information quality. Silica, it turns out, has a very low optical nonlinearity. And in many ways, it is the ideal material for doing transmission of optical signals because it has low loss, the optical nonlinearities are very low. But now we're building communication systems that go thousands of kilometres. So even though the optical non-linearities are very low, when you send your signal 1,000 kilometres, it accumulates, these non-linearities accumulate and build up, and they can introduce significant, what we call in the business, penalties that reduce the quality of the signal. Well, so we've talked about glass optical fibres. It turns out there are a whole range of materials that you can make a fibre out of, and I'll give you a couple of exciting examples that are solving somewhat different problems. My group is working on fibres that are made out of a different type of glass altogether. It's called a chalcodrenite glass, and it doesn't have silica. It's based on arsenic and selenite, pretty nasty materials. But the reason this material is very important is because it's transparent, which means it can transmit wavelengths out in the mid-infrared. And the mid-infrared is a part of the spectrum that is very important for a number of applications in defence and sensing. So making fibres that transmit in the mid-infrared is very attractive for those applications. Another example are colleagues of mine who are making fibres out of plastic or polymers. And whereas they don't have the transparency of silica, they have some other very attractive properties. In particular, the low melting temperature means that their fabrication is much easier. They open up applications in very short distance optical communication systems. And I'll give you another example where fibres are becoming common, and that's in automobiles, where polymer or plastic fibres are used to communicate within the automobile itself.